Welcome to the Explainer. Most of the time we think of speaking as just this entirely organic, kind of messy human habit, right? But today, we're actually going to look at human language totally differently. We're looking at it not just as a random collection of sounds we make with our mouths, but as a highly mathematical, algorithmic code. It's literally running quietly in the background of our minds every single time we speak. If you peer right underneath the surface, you'll find a rigidly structured system that behaves way more like a computer program than a biological reflex. Now think about this tiny, almost microscopic number, 0.005%. That right there is the mathematical probability that a randomly selected set of linguistic sounds makes any logical sense together. Basically, if you just grabbed a handful of random consonants and vowels, there is almost zero chance they'd form a valid, cohesive group according to the rules of human language. So what does this tell us? It means the sounds we use aren't random at all. They're meticulously curated by these incredibly strict underlying laws.
Section 1. Sounds and Natural Classes. To really wrap our heads around why that percentage is so staggeringly low, we have to look at the inputs of language. And we're going to start with an amazingly logical, ancient system. Sanskrit. Now, the Sanskrit alphabet was arranged with pure mathematical precision way before modern linguistics was even a thing. The distinct sounds of the language, the phonemes, were brilliantly organized by specific physical attributes, like, is the sound made with the lips? Do the vocal cords vibrate? Does air pass through the nose? Anytime you group sounds purely by these shared feature rules, you create what linguists call a natural class. Think of it like a logic gate in programming. A sound either fits the exact specific criteria or it doesn't. No exceptions. And that brings us right back to our math. If you take just 25 Sanskrit phonemes, mathematically speaking, you could combine them to create over 33.5 million completely random sets. But the moment you apply the strict logic of those linguistic attributes, say finding only the sounds that are both retroflex and voiced, you get exactly 162 valid, rule-abiding natural classes. That's it. Out of over 33 million possibilities, only 162 are actually legal in the hidden code of phonology.
Section 2. The Mathematics of Sandy.
Let's actually see how this builds into a functioning algorithmic system by looking at something called sandhi. Sandhi is this wild phenomenon in Sanskrit where the sounds at the end of one word physically mutate depending on the sound at the beginning of the very next word. It's kind of like the words are reacting to each other chemically. If you open up a traditional grammar textbook, you'll usually be confronted with this terrifying 154-case lookup table of mutations. It'll outline things like a K magically becoming a G or a T turning into a D under very specific conditions. Honestly, it seems like it would require pure agonizing rote memorization. I mean, how on earth could a speaker's brain compute all of that on the fly?
Well, here's the absolute game changer. They aren't memorizing 154 random changes. By leveraging those natural classes we just talked about, all 60 of the actual sound changes happening in that massive table can be elegantly condensed down into just 8 algorithmic rules. Just 8. Because our mental language software doesn't say, change a K to a G before a B. It says something way broader and smarter. Change any voiceless stop to a voice stop if it sits next to another voice stop. And that brilliantly illustrates the core formula of phonology. Input X becomes output Y whenever it happens to be found in the specific context between C and D. That's the literal syntax of the language code. It is a precise, logical statement that gets executed by our brains in actual milliseconds, long before the sound ever even leaves our lips.
Section 3. When sounds disappear.
Okay, so let's apply this exact same codebreaker logic to a modern language, like German, to uncover how these linguistic rules actively hide letters from us right in plain sight. It completely proves that what we hear isn't always what's actually there. Let's consider 2 German words. One means wheel, and it's spelled with a D. The other means advice, and is spelled with a T. They're visibly different words, right? But if you listen to a native speaker say them, they are pronounced exactly the same on the surface. Caught. The D in wheel is completely gone, totally replaced by a T sound.
So, why does that happen? It's because German has this widespread background process running called final devoicing. The rule basically dictates that voiced stops, like the letter D, lose their voice feature whenever they hit the end of a syllable or word boundary. The vocal cords just turn off. So the word for wheel enters the brain's processor with a D, hits that end of word boundary, triggers the devoicing rule, and boom, it outputs a T. But here is exactly where the underlying code reveals itself. When we make these words genitive by adding a suffix, so we're making them of the wheel or of the advice, The hidden D in the word for wheel suddenly reappears when spoken. It becomes raudes. Why? Well, because by adding that extra syllable, that D is no longer sitting at the very end of the word. The specific condition for the devoicing rule just isn't met anymore, so the true underlying D is finally allowed to be spoken out loud. Pretty cool, right? Section 4. Deep versus surface reality. This whole German mystery honestly forces us to rethink everything we know about how language is actually stored in our brains. It implies that the sounds we physically make are often just an illusion, a byproduct created by real-time processing. Because of these invisible mechanics, linguists propose that we're actually operating with two entirely separate realities at once. First, there's a deep, highly regular phonological representation stored in our minds. This is the reality where wheel always has a D. And then there is the surface representation. That's the messy, physical reality of what we actually speak, where that D sometimes mysteriously turns into a T. So our brain essentially stores the simple, regular, deep sequence because it's super efficient for memory storage. It only contains the absolute minimum specifications needed. But right before we speak, our mental software runs a series of what we call realization rules. These rules act like a bridge, actively executing mapping algorithms that generate the context-dependent surface output. You are quite literally compiling code every single time you open your mouth to say a sentence.
Section 5. The mouse and mice problem.
All right, let's dive into this final puzzle. How on earth does our internal language software handle extreme rule breakers? What happens when a word just completely defies standard operating procedures, like the English plural? Now, if phonology were purely based on easy articulation rules, making plurals would be a total breeze. The plural of cat is cats, the plural of dog is dogs. So logically, the plural of mouse should obviously just be mouses, right? It's perfectly fine phonologically to say it that way. So why doesn't English do that? Why does the internal root vowel completely change its identity to give us mice? Linguists have actually proposed 3 main code-breaking theories to solve this little conundrum. Theory 1 is simple. We just memorized mouse and mice as entirely separate words with no root connection whatsoever. Theory 2 suggests the root just happens to have 2 alternate forms that we swap out. But Theory 3 introduces a wild, highly mathematical concept that treats human language exactly like computer programming. Theory 3 relies on something called the archiphonium. And in this theory, the root vowel isn't stored in our brain as the ow in mouse or the I in mice. Instead, it's stored as an undetermined, totally flexible lower high vowel in our deep code. Think of it as an incomplete variable. It's essentially a blank space sitting right in the middle of the word, just waiting for a command to tell it what it's supposed to be. Think about how incredibly elegant this sequence is. In this system, the concept of plural in English isn't an S sound at all. It's actually an invisible command symbol. When you decide you want to talk about more than one mouse, your brain deploys a plural command that searches backward, finds that flexible, blank archiphoneme vowel, and literally forces it to shift its phonetic features to the front of your mouth. So the plural is actually an algorithm actively rewriting the root word in real time. Mind-blowing, right? So as we wrap up this explainer, I really want to leave you with this thought. The next time you say a simple word, or change a noun to a plural, take a second to consider the incredible mathematical code running quietly in the background of your mind. Ask yourself, when you communicate, are you just making noises born of simple human habit? Or are you executing a complex, beautiful series of mental algorithms that bridge the gap between your deep mind and the surface world? Thanks for joining me on this deep dive.